Lesson 5.9, application of exponential and logarithmic, I should say, functions. So in grade 11, we did application of exponentials. All right, so you think about like half-life or bacteria doubling, those type of problems. So we're just expanding on those concepts in this one, and we're expanding on it by using logarithmic functions. So as a recap from what we've done in previous years, let's go over this general exponential equation. And this general exponential equation is really how these like subsets are created. Okay, so like doubling, tripling, half-life, and percent growth are really just different ways of writing this. Okay, and it really boils down to changing the base. Like what type of problem is it? Is it a half-life, right, where that would be half? Is it triple, where this would be 3? And so we'll create those formulas in a second, but you're not given these on the exam or the test, so you do have to know how they're created, but it really is just this same equation, and you're just changing this value, okay? All right, well, let's define some of those variables that we see up here. That way we can create these equations down here. So what's on the left side, like what this whole exponent is equal to, the y, well, this would be the final amount, okay? Like an investment, like how much money is left over, or just, bacteria double, like how many bacteria after 10 years, like those type of problems. So what do you have at the end? A would be what you start with. This is the initial amount. And as I just said, the B is the factor. Like, is it doubling? Is it halving? Is it tripling? So this is your growth factor. Growth, or I should say decay factor. Because it could be like halving, right? Decaying. And then the X up top here. This is just how many times this factor is applied. So this is how many times are you applying a double or a half. So it's the number of growth periods. Right, like if you saw like a problem where it was like 2 to the 3, this means you have some initial amount, A, that is going to be doubled, and then it's going to be doubled again, and then it's going to be doubled again for a total of 3 times, right? So there are 3 growth periods where your amount is doubling. Okay. So now let's use that general one, and let's create some other subsets of that general. So we have the doubling. Well, the doubling, notice that the base is 2. But we have adjusted the exponent here, t being divided by little t, all right? Well, that is really just the same thing as x, and it's just how many growth periods there are, where t, little t, is just the total time that's gone by, total time elapsed. And big T, well, that is the time for one growth period. For one growth period. Okay? And if we just think about what this fraction is, right? Like, let's say the problem was doubling, okay? Like you have bacteria doubling. And I say that the bacteria are going to double for 10 years, okay? But let's say that it takes 2 years for them to double. Well, that means like 2 years has to go by before you get your first doubling. And that means another 2 years goes by, so for a total of 4 years for the next one to happen. So how many doubling occur in the span of your 10 years? So let's just keep going. 8 years, 2, for a total of 10 years. Well, you can see that we'd have 1, 2, 3, 4, 5 doublings that happen. That's because it takes 2 years for every doubling to occur. That's why this is the time it takes for one growth period. Okay, so yes, the experiment was running for 10 years, but so that is not me saying, hey, you're going to double 10 times because it's running for 10 years. You have to account for the fact that you have this growth period, okay? So let's just get rid of that because we're going to run out of room if I leave that up there. The other thing I want to just note is that these both variables here have to be in the same units, okay? So that means you're either working in hours, minutes, seconds. It is a time, so just make sure you're using units of time, but they need to be the same units of time. And then we can see that we also have these other two variables, n naught, and really those are just the same thing as y and a, okay? All right, so n is your final amount, and n naught is your initial amount. And similar to time, these need to be in the same units. Like if the problem is saying your money is doubling, right? You're starting with money, it's not like you can end up with like milligrams or something like mass. It's like, no, you got to be both in units of dollars. Okay, so there is your doubling one. That one is given to you. Well, let's just use the same logic to create a tripling one. Well, I'm going to have some initial amount, some amount. And what I'm telling you is that, well, you're going to triple it, so you're going to multiply it by 3. Well, how many times am I multiplying it by 3? Well, how long do you want me to run the experiment for? And then how often am I applying a tripling? That's the big T. And then once you know those values, well, that's just going to be equal to whatever the final amount is, however long this experiment ran for. So half-life, well, same idea. I'm going to have some initial amount, and I'm saying have it. Okay, so you're going to multiply it by half. Well, how long am I running this for? So little t. And then how often does a half-life occur? Big T. And then once you know those, that's just going to be equal to some final amount. And then the fourth subset of the general equation is your percent growth. And I should add decay here. And the only difference between growth and decay when it comes to percentage is that if it's growing, it is a positive. So I'll just put that in purple. And so let's make this purple so you understand the difference. And then if it's decaying, you're just subtracting the interest rate. And actually we should define I because that's the last variable we have. I is just the percent represented, percent of growth or decay. But make sure you put it as a decimal. All right, let's just get right into the problems. We have 3 examples that we're going to be doing in this lesson, so it is a short lesson. But yeah, let's just get right into it. Lana has purchased a minivan for $24,000. The value V in dollars of the minivan depreciates 50% every 3 years. Determine an equation that represents the value of the car in dollars as a function of time t in years. So it's defining our variables for us. We have some value V, so think of that as like your Y. So you're going to have some value V, and it's telling you that the value is dependent. All right, so this is your dependent variable on t. So your function you're creating is V of t. All right, well, you can see that we're given a percentage, so I'm most likely going to be using this one right here. And it's saying it depreciates by 50%. So depreciates by 50%. This tells you that you're decaying. You're decaying, and it tells you that the I is, well, represent 50% as a decimal, 0.5. It's saying that the minivan was purchased for $24,000. So that's your initial amount. That's N naught. or I guess v naught technically, because we're using v as our variable. So v naught. And every 3 years, that depreciates, that 50% is depreciated. So let's fill in our blanks. We have VT, well, let's just start with just writing the general out, V naught. This is a decaying problem, so it's going to be 1 minus the interest rate. And then you're going to have some time that's elapsing, and then how often does this interest rate get applied? So we're creating the V of t equation. We were given a amount of $24,000. That's what you bought it for. It depreciates by 1 minus 0.5. And then every 3 years that depreciates applies. So that is the big T on the bottom. So you can see color-coded, right, where all those pieces of information came from. Just last step, just don't leave it like this. Make sure you evaluate that bracket. So your final answer would just be VT is 24,000, 0.5 T over 3. Okay. Part B. How long will it take for Lana's minivan to depreciate to $15,000? So essentially this is saying, hey, I'm giving you the final amount. I'm telling you that V of t is equal to 15,000. And the question says, how long? So meaning, I'm asking you for what is the time? You're solving for little t. So if we have our equation, which is just reading from above, 24,000, 0.5 t divided by 3, I am just substituting in 15,000 for my left side of my equation, 24,000. And then the only unknown in this problem is now that little t in the exponent. So let's rearrange the problem so we can isolate for little t. So step 1, I need to divide both sides by $24,000, or 24,000. So both sides get reduced. So that and that will cancel, and you're going to have 15,000 divided by 24,000. So just put that on your calculator, and you're going to find that that is 0.625, and that's going to be equal to 0.5 t divided by 3. All right, and again, what makes this grade 12, all right, you've seen this in grade 11 where you had to solve for this exponent, but what makes it grade 12 is the fact that there is no way to write these and these as the same base and solve for that exponent. So now you need to actually use logarithms. So I will apply a log to both sides. So I'm going to run out of room, so I'll do it on the next line down. 0.625, I'm going to apply a log to that. And I'm going to apply a log to 0.5 t to the 3. And this allows me to take this exponent down in front. So I will get log 0.625 equaling t over 3, sorry, that's a t, t over 3 multiplying log 0.5. So now we need to isolate for t, so I'm going to get rid of log 0.5, 0.5, and make sure you divide it on this side as well, log 0.5. So this and this cancel, and let me just work over here. So on the left side, I have log 0.625, that is being divided by log 0.5, and that is equal to t over 3. So last step, it would be multiply both sides by 3 to get rid of the 3 on the bottom, and you get t on its own, and t on its own would be the equivalent of 3 multiplying log 0.625 divided by log 0.5. So that is t. Just put all this in on your calculator. All right, and try it, see if you get my same answer. T will approximately equal 2.03 3, 4. And what are my units of time? Years. So that is how long it will take for the minivan to equal $15,000. Part 2 of B. When will it be 25% of its initial amount? Well, if it was initially $24,000, and if I want a quarter of that, so 25%, well, that's like me saying, okay, well, when is it going to be equal to a value of $6,000? Because that's what a quarter of 24,000 is. So you set up the problem the exact same way. This is like your final amount. You're solving for t. So that is what v of t is. And you are solving for t. So set 6,000 equal to your equation. All right, we're just pulling the equation from right here. So 6,000 is equal to 24,000, 0.5 t over 3. And you would do the same way. You would divide by 24,000 on both sides. But you can already see, like, there would have been a faster way to do this, that you know that you're going to a quarter. So quarter per, like 25% would mean that n divided by, n naught divided by n, or sorry, other way around. N divided by n naught is 1/4. Like, that's what 25% is. So like this is n, this is n naught. So when we do our simplification, we are going to get 1/4, okay? And the reason I am saying that is because sometimes problems in the homework won't tell you what the initial amount or the final amount is. They're just going to simply say, solve for when it is a quarter, and you don't know how much it is worth or how much it is started at. But all I care about is when is it going to be the quarter amount, okay? Notice that you could have got to this quarter even if you didn't know what 24 is or what 6 is. I could have just taken my equation and just said, hey, well, a quarter is equal to my base to my exponent. So my quarter is equal to my base being 0.5 to the t over 3. And now you're going to do the same thing we did in the previous problem. All right, you can take the log of both sides and solve for t, or you can recognize that this is 1/4. This is technically 1/2 t to the 3. Well, I'm going to go faster because I know that quarter and half, I can actually write these as the same base. This is the same thing as me saying 1/2 to the 2, 1/2 to the t over 3. So you don't always have to use logarithms, okay? So sometimes there is a faster way to do it. And if that's the case, now I have the same base. I'm just going to equate my exponents. So if 2 is equal to t over 3, or t is 6 years. So it takes 6 years for the minivan to be a quarter of its value. Question 2. An antique coin appreciates in value at 7% per annum. Per annum just means per year. Per year. And it's telling you that it's appreciating, so that means it's growth. And this is the interest rate. That's what that's giving you. That's I. So the question says, if it was purchased in 2002 for $1,200, how much will it be worth in 2008? Okay, so in 2002, let's like, why is it telling me 2002 and 2008? Well, it's saying that if this is the initial time, right? Like, this is when the problems start. How long has gone by? So these two pieces of information here, 2008 minus 2002, means that 6 years. 6 years has gone by. Well, which variable represents, so that's years. Which variable represents time elapsed? Well, that's little t. So little t is 6. So if it was purchased in 2002 for $1,200, how much will it be worth in 2008? All right, so how much will it be worth? Well, that's asking for the final amount. So let's create an equation. All right, we have some final amount y being equal to your initial amount, 1200. That is being multiplied by, this is a growth and it's a percentage. So it's 1 plus 0.07, because I, when you take that and you put it in a decimal, is 0.07. And that is being put to the power of 6. And then there would be a big T here. So what is that big T? Well, it appreciates in value at 7% per annum. So this per annum part right here, this is telling you that T is 1. Every year your thing grows by 7%. So this is really just 6 over 1, or just 6. So then that is 1200 multiplying 1.07 to the power of 6. And then you do that, you will get a y value of, or a dollar value of 1,888. Right? You don't keep going in decimals. Right? Think about the problem. This is a dollar, so the max you can have is a single cent. Right? So 2 decimal places. So here you go. When will it be worth 2,000? So when, that's me saying, hey, solve for little t. And when will it be worth 2,000? Well, that's your final amount. So that's making me saying, hey, I'm giving you y now in this problem. Y is 2,000. So I'm going to say 2,000 is equal to my initial amount being 1,200. It's the same problem, so it's the value is still growing by 7%. But now I'm just solving for t. I'm not telling you how long time has elapsed. So isolate for t. So we're going to divide both sides by 1,200. So 1,200, 1,200. And on the right side, you're going to get 1.67, like essentially 20 over 12, which would reduce to 5 over 3, or 1.67. And that's going to be, I'll rewrite that number so it's cleaner to look at, 5/3. And that's 1.07 to the power of t. And now you need to apply your logarithms to both sides. So we are going to have log 5/3. Right? And by the way, it would have been okay if you just put 1.67. Like, that's fine. So log 5/3 is equal to t log 1.07. And so if I'm isolating for t, I am going to divide both sides by log 1.07. 1.07. Those cancel, and you get t is equal to log 5 over 3 divided by log 1.07. And that will give you an approximate answer of 7.55 years. So when will it be worth $2,000? Well, 7.55 years has to go by, and you bought the car in 2002, so 2002 plus 7.5 years essentially, right? So that means that it's going to be 2009 and halfway through the year, right? So whenever you get to this point, it's like halfway through the year, you just go to the next year up, right? So just go to the next year. So in your final answer would be in 2010. Okay, so in 2010, this car will be worth $2,000. So final answer is in 2010, the car is worth $2,000. Because if you put 2009 here, that wouldn't be the case, because you had to go halfway through the year to be able to get it. So it's not 2009, it's 2010. Last problem. The time it takes an oven to preheat is given by the formula little t, all right, so time, is equal to 3 log 0.1 big T minus 2 over log 2, where t is the time, so it's defining the variables for us. In this case, capital T, big T is temperature in Celsius, at which the oven is, time in minutes T in degrees Celsius, at which the oven is set. Okay, that's fine. How long will it take to preheat an oven to 350 degrees Celsius? So it is giving you the final temperature. So it's saying how long will it take. So it means like this problem is saying calculate little t. And it's giving you what big T is. This is saying big T is 350 degrees. So those are really the only two variables that we have in the problem, right here and here. So let's just plug it in. We have little t equaling 3 log 0.1, and big T, it told us it was in Celsius, so we can literally just directly substitute that in. So 350 minus 2 all over log 2. So this is just a calculator problem in essence. So just put that all in your calculator and hit equals, and try putting it in your calculator yourself, and let's see if you get the same answer, because again, bed masses, every calculator is different on how it asks you to input numbers, but you should get roughly 15.133. Okay, so approximately, does it say how long to round to? Nope, so just approximately 15 minutes if I just round to the nearest minute. If it takes 16 minutes to preheat the oven, what was the temperature setting for the oven? All right, so now it's kind of the opposite direction, or opposite variable we're solving for. It's giving you little t. Oh, so t is 16. And what was the temperature setting? So what was the temperature? That aspect is asking you what is big T. So we have our formula, which is t being equal to 3 log 0.1 t minus 2 all over log 2, and it is giving you a little t value of 16. So that's 16 is 3 log 0.1 t minus 2 all over log 2. And all we're going to do now is just rearrange this problem and isolate for this variable on the inside. So my first step is I need to get rid of this log 2 that's on the bottom here. So I will multiply both sides by that log 2, which will get me 16 log 2 is equal to 3 log 0.1 t minus 2. Now I need to get rid of this 3 here. So I will divide both sides by 3. And I get 16 log 2 over 3 is equal to log 0.1 t minus 2. Well, evaluate this, because this whole thing is going to be an approximate. So if you evaluate that, what is that? That's log 2 divided by 3 times 16. That is 1.605 is equal to log 0.1 t minus 2. So we're isolating for the inside of a log. That means turn that into exponential. So take the base of the log and put it to the power of that. So that base, because we don't see a number, is really just 10. So that's me saying, hey, take 10 and put it to the power of 1.605. And that will be equal to 0.1 t minus 2. So 10 to the power of 1.605, 10 to the power of 1.605, that's 40.27. 40.272 is equal to 0.1 t minus 2. So bring the 2 over. 42.272 is 0.1 t. And then divide both sides by 0.1. So essentially you're just shifting the decimal place 1 unit over. So that would be 422.72 degrees Celsius. And it didn't really tell us an approximation, so you're not really going to set your oven for a decimal. So let's round it up. 423 degrees Celsius. Alrighty. That is the lesson. Bye for now. See you in class.